So let's take a look at the fundamental theorem of calculus. Now before I move on to the actual fundamental theorem, I'm going to start by talking about antiderivatives and derivatives. Obviously antiderivatives, because it has anti in front, it's going to be the opposite of derivatives. And remember, integrals are also the opposite of derivatives, so antiderivatives and integrals are basically the exact same thing. Now similar to some derivative formulas, we also need to memorize some antiderivative formulas. So the first one here is we have x raised to some power n, and n cannot be equal to negative 1. Now similar to how there was a power rule for derivatives whenever we derived x to the n, there's also a power rule for integrals when we integrate or when we take the antiderivative of x to the n. And the formula for that is going to be x to the n plus 1 over n plus 1. So in the derivative power rule, we brought the power down and subtracted the power by 1. But in the antiderivative, or when we take the integral of x to the n, we add the power by 1 and divide by the same power. Now the next function we have is x to the n, but this time when n is exactly equal to negative 1. So in this case we have x to the negative first power, or 1 over x. Well, in order to think about the antiderivative, we need to think about what do we take the derivative of to get 1 over x. Well, remember we did take the derivative of the natural log of x. The derivative of natural log of x is equal to 1 over x. So if the derivative of natural log equals 1 over x, then the integral of 1 over x is natural log. But be careful here because it's not just going to be the natural log of x, it's actually the natural log of the absolute value of x whenever you take the antiderivative of 1 over x. So just remember that. Now the next function we have is e to the x. Well, remember the derivative of e to the x is e to the x, so the antiderivative of e to the x is also e to the x. So this one's pretty easy to memorize. Now the next function here is going to be cosine of x. Well, what do we take the derivative of to get cosine of x? Well, we took the derivative of sine of x to get to cosine x, so the antiderivative of cosine x is going to be sine of x. Now for the next one, what is the antiderivative of sine of x? Well, the derivative of negative cosine of x is equal to sine of x, so the antiderivative of sine of x is going to be equal to negative cosine x. If I go ahead and write that down. Okay, now for the next function, we have secant squared of x. Remember the derivative of tangent x is secant squared, so the integral or the antiderivative of secant squared is tangent x. Now for the next one we have secant x tangent x, and remember we took the derivative of secant x to get to secant x tangent x, so the antiderivative of secant x tangent x is going to be secant of x. So really the only new rule here is the power rule, because we haven't learned that before. But for everything else, we just need to think about what do we take the derivative of to get the antiderivative. Now moving on to the actual fundamental theorem of calculus, I'm just going to go ahead and label that FTC. There are actually two parts to this fundamental theorem. So the first part of the fundamental theorem of calculus, just go ahead and label that number 1. Let's say we have a function g of x, and it is equal to the integral from some constant a to the variable x of f of t dt. Now the next step here is to derive both sides. So the derivative of g of x is g prime of x, and that's going to equal, now the variable here is x, so we're going to derive with respect to x the integral from a to x of the same exact function, f of t dt. And once again, derivatives and integrals are opposites. So on the left side of the equation we have g prime of x. On the right side, because once again they're opposites, they will cancel. And all you have to do in this case is take the top bound, which is the variable, and sub it into the function. So all you have left is just f of x. Now let's say I rewrite it, so we have g of x equals the integral. We still have the a on the bottom, but on the top bound, instead of just x, we have u, some other function. So it might be something other than x, like x squared plus 5 or x cubed of still f of t dt. Well, when you derive both sides, you get g prime of x equals, I'll still rewrite the derivative, so derivative with respect to x of the integral from a to u of f of t dt. Now when you derive, it's going to be very similar to the chain rule, where obviously derivative and integral will still cancel. The u, we're going to sub it in for the t in the function, so g prime of x equals f of u, and because we have some inside function other than just x itself, we have to multiply by the derivative of the inside function, similar to the chain rule, or multiply by u prime. Now one more thing to keep in mind is always make sure that the integral is in the form where the bottom bound is a constant. It doesn't matter what the constant is, it just has to be a constant, and the top bound is the one with the variable. Because when you go ahead and take the derivative, like we did in this example here, the bottom bound doesn't matter. All we do is we sub in the top bound, which is the variable, into the function for t. Now moving on to the second part of the fundamental theorem calculus, let's say you have the integral from a to b of f prime of x dx. Now the way you evaluate this integral, all you have to do is take f of b minus f of a. And this leads me to explain how you evaluate an integral. So if f prime of x is a derivative, the antiderivative of f prime of x is just going to be f of x, right? So when we take the integral of f prime of x, we're going to get f of x. And now in order to evaluate the integral, all you have to do is you can draw a bracket, or you can draw a straight horizontal or a vertical line, and then you write down the bounds. So in the exact form. So the bottom bound is a, the top bound is b. Now to evaluate this integral, you just plug in the top bound first, so f of b, and then minus when you plug in the bottom bound, f of a. And that exactly matches the formula, and that's how you evaluate integrals. Now for this first set of problems, let's use part 1 of the FTC to find the derivative of the function. So for number 1, we have g of x equals the integral from 0 to x of the square root of 1 plus 2t dt. So once again, using part 1 of the fundamental theorem of calculus, we have to take the derivative of both sides. So we have g prime of x on the left side of the equation equals, our variable is x, so we're going to derive with respect to x the integral from 0 to x of the square root of 1 plus 2t, I'll rewrite that, 1 plus 2t dt. Now once again, derivatives and integrals are opposites, they will cancel. Make sure that the bottom bound is a constant, which it is, and the top bound is a variable, which it is. So we can go ahead and evaluate. So g prime of x equals, once again, all we're doing is we're subbing in our variable into the function for t. So all we have left is the square root of 1 plus 2x. And that's it. That's the final answer. Now for number 2, we have g of y equals the integral from 2 to y of t squared sine of t dt. Now realize instead of the x variable, we do have the y variable, but that doesn't matter, we treat it the exact same way. First step, as always, we take the derivative. So g prime of y equals, now our variable is y, so we're going to derive with respect to y. The integral of the same exact thing as above, for the integral from 2 to y of t squared sine t dt. Now before we evaluate, we have to make sure the constant's on the bottom, which it is, and the variable y is on top, which it is. So we can go ahead and take the derivative of the integral. Once again, they are opposites, so they will cancel. All we have to do is plug in y everywhere into the function for t. So we have y squared times sine of y, and that's it. Now for number 3, we have f of x equals the integral from x to 2 of cosine of t squared dt. First step, as always, we derive. So f prime of x on the left side of the equation equals our variables x, so we derive with respect to x, of the integral from x to 2 of cosine of t squared dt. Now before we evaluate, we have to make sure in the integral, once again, the variables on the top bound, the constants on the bottom bound. In this case, the variables on the bottom bound and the constants on the top bound. That's the opposite. But remember the flip-flop rule, where let's say you have the integral from b to a of f of x dx. Well, that's the same thing as saying negative 1 times the integral from a to b of the same function, f of x dx. So if you flip the bounds, you have to multiply the integral by negative 1. So we can use that exact same property here, where I'm just going to go ahead and rewrite f prime of x equals the derivative with respect to x of the negative 1 times the integral. We're going to flip the bounds. So this time, instead of x to 2, we have 2 to x of cosine of t squared dt. Now the negative is just a constant, so I can take that outside the derivative and rewrite it as negative 1 times the derivative with respect to x of the integral that we've just written down. And so now I can go ahead and evaluate. So f prime of x equals, we do have a negative on the outside, so we'll just include that negative there. Derivative and integral will cancel. I have to sub in the x into the function for t. So what we have left is negative cosine of x squared. Now for number 4, we have f of x equals the integral from x to 10 of tangent theta d theta. Realize once again we do have the variable on the bottom bound, the constant on the top bound. So even before we derive, we can also flip the bounds. So f of x is going to equal negative 1 times the integral, this time from 10 to x, of tangent of theta d theta. Now that the variable is on top, or on the top bound, we can go ahead and evaluate. So when we derive f prime of x equals, now negative is just a constant, so I can take that outside of the derivative of the integral from 10 to x of tangent of theta d theta. Once again, derivative and integral will cancel. All I have to do is put the variable into the function, this time not for t but for theta. So f prime of x equals, we do have the negative outside, so negative tangent of x. And that's the final answer. Now for number 5, we have h of x equals the integral from 2 to 1 over x of inverse tangent of t dt. Now the constants on the bottom, the variables on the top, so we can go ahead and derive. So h prime of x equals, now our variable is x, so we're going to derive with respect to x, the derivative with respect to x of the integral from 2 to 1 over x of arctangent or inverse tangent of t dt. Now, h prime of x, once again the derivative and the integral will cancel. Once again, all I have to do is take 1 over x and sub that in for t. So we get arctangent or inverse tangent of 1 over x. Now realize that our function here is something other than x. It's 1 over x. So it's similar to the chain rule where we have to multiply by the derivative of that inside function. So the derivative of 1 over x, I can go ahead and rewrite that as x to the negative first power. We can just use the power rule and we'll get negative 1 x to the negative second, or negative 1 over x squared. So we multiply by the derivative of 1 over x, which is negative 1 over x squared. And that'll give us the final answer of negative arctangent of 1 over x all over x squared. Now for number 6, we have g of x equals the integral from 2x to 3x of u squared minus 1 over u squared plus 1 du. Now the first thing we realize here is that we have variables on both the top bound and the bottom bound, and we cannot take the derivative of the integral in that way. So what we must do is divide this or split this into two different integrals. And so the way you do this, we write g of x on the left side of the equation equals, now we write the first integral, we take the bottom bound, that's going to be the bottom of the first integral, so 2x. And then on the top bound, it's going to be some constant a, just assuming that a is going to be in between 2x, the top or the bottom bound, and 3x, which is the top bound. And also remember that, similar to the previous problems, when we took the derivative of the integral, the constant didn't matter. The only thing we sub into the function is the variable itself, not the constant. So we have the integral from 2x to a of the same function u squared minus 1 over u squared plus 1 du, and then plus the second integral. And the second integral, this time the bottom bound is going to be a, and the top bound is going to be the top bound of the original integral, so 3x, of that same function, u squared minus 1 over u squared plus 1 du. Now the good thing is this is the same process you use every time you're trying to find the derivative of the integral, and both bounds of the integral are variables. Now before I find the derivative, notice that for this first integral here, the bottom bound is the variable, the top bound is a constant. So we need to flip that so the constant is the bottom bound. So I'm going to rewrite it as g of x equals negative 1 times the integral, this time from a to 2x, of u squared minus 1 over u squared plus 1 du, and then I can just go ahead and rewrite the second integral because once again it is in the correct form. So plus the integral from a to 3x of u squared minus 1 over u squared plus 1 du. So now we can go ahead and derive both sides. So we have g prime of x equals, now we can derive each individual integral because there is a plus sign separating both integrals. So we have negative derivative with respect to x. Once again, that negative can come outside the derivative of the integral from a to 2x of that same exact function, u squared minus 1 over u squared plus 1 du, and then plus the derivative with respect to x. Once again, the integral from a to 3x this time of u squared minus 1 over u squared plus 1 du. So now evaluating here, g prime of x equals, we do have a negative, so I'll include that negative right away. Derivative and the integral will cancel. The constant doesn't matter, all I have to do is plug in the top bound, or that includes the variable, into the function for u. So we get 2x squared minus 1 over, once again, 2x squared, this time plus 1. And notice we have something other than x, we have 2 times x, so we have to multiply by the derivative of 2x. And derivative of 2x is just going to be 2. Now plus The second integral here, the derivative and the integral will cancel. I'm just going to plug in 3x into the function. So then we get 3x squared minus 1 over, same thing, 3x squared, but this time plus 1. And because we have something other than x, we have 3 times x, we have to multiply by the derivative of that inside function. And derivative of 3x is just going to be 3. So now further simplifying here, g prime of x equals, we do have a negative. Now 2x squared is going to be 4x squared. So 4x squared minus 1 over 4x squared plus 1, and then times 2. And then we have plus 3x squared, which is going to be 9x squared, minus 1 over 9x squared plus 1. And we do have that 3 that's being multiplied by 9x squared minus 1. Now if you want to simplify further, you can, but this is basically going to be the final answer. Now for these next set of problems, let's use part 2 of the fundamental theorem calculus to evaluate the integral. So for number 1, we have the integral from -1 to 3 of x to the 5th dx. Now remember that the second part of the fundamental theorem calculus is that the integral from a to b of f prime of x dx is equal to f of b minus f of a. This is basically giving us how to solve or how to evaluate the integral. First we antiderive, and then we evaluate by plugging in the bounds. In other words, we plug in the top bound first, and then minus when we plug in the bottom bound. So let's go ahead and evaluate this integral. Now the integral of x to the 5th, remember that this is in the form x to the n. So the integral, or the antiderivative of x to the n, we're going to use the power rule formula for integrals, where we add the 1 to the power and divide by the same power. So the integral of x to the 5th is going to be x to the 6th over that same power. Once again, we add the power by 1, divide by that same power. So now that we have antiderived, we have to evaluate using the bounds. So we can either draw a bracket like this, or we can draw a straight vertical line, and then we include our bounds. So the bottom bound is -1, top bound is 3. Once again, we're going to use the fundamental theorem calculus, f of b minus f of a. So we're going to plug in the top bound first, 3 for x, and we'll get 3 to the 6th over 6, and then minus when I plug in f of a, so the bottom bound, -1, in for x. And that's going to be -1 to the 6th over 6. Now to further simplify, 3 to the 6th is going to be 729. So we get 729 over 6 minus, now -1 to the 6th is going to be +1 over 6. 729 minus 1 is going to be 728 over 6. And for our final answer, we can divide both the numerator and denominator by 2 and simplify that fraction down into 364 over 3. Now for number 2, we have the integral from 2 to 8 of 4x plus 3 dx. Because we do have a plus sign separating 4x and 3, we can take the integral of each individual term. So the integral of 4x, we can still use the power rule because 4x is basically 4x to the first power. So in order to antiderive, we add the 1 to the power, so 4x squared, and divide by the same power. So then 4 over 2 is 2, so then the antiderivative is 2x squared. You can also double check by deriving this and see if you get back to 4x. Well, the derivative of 2x squared is going to be bring the power down, 4x, and then we subtract the power by 1 to the first, which is obviously 4x. So we know, that way we know we have done it correctly. So we get 2x squared, and then plus the antiderivative of 3. Now obviously when you take the integral of a constant from a to b times dx, remember we can use the formula where we take the constant times b minus a. Now another way you can do this, let's say you have the integral from a to b of a constant times dx. All you have to do to integrate is take the constant times the variable of integration. The variable of integration is x, so we just get the constant times x, and then we can go ahead and evaluate from a to b. Now if your constant, or if your variable of integration, let's say instead of dx we have dy, then it's just going to be the constant times y. It works with any variable, but just make sure that when you integrate a constant, you can either use this formula, or you can take the constant and multiply by the variable of integration and evaluate from a to b. So in this case, the integral of 3 is just going to be 3x, or the antiderivative of 3 is 3x, and then we can evaluate from the bounds of 2 to 8. So plug in 2 as the bottom bound, 8 as the top bound. So when we evaluate, we first plug in 8 into the function, so we get 2 times 8 squared, which is 64, plus 3 times 8, 24, minus when I plug in the bottom bound into the function, so when I plug in 2, I get 2 times 2 squared, which is 4, 2 times 4 is 8, plus 3 times 2, which is 6. Now we get 2 times 64, which is 128, plus 24, and then minus 8 plus 6, which is 14. 24 minus 14 is 10. 10 plus 128 is 138, and that's the final answer. Now for number 3, we have the integral from 0 to 1 of x to the 4/5 dx. Now we can still use the power rule here, or if we have x to the 4/5, all we have to do is add 1 to the power and divide by that same power. So x to the 4/5, when we take the antiderivative, we add 1 to 4/5, which is going to be 4/5 plus 5 over 5, which is 9 over 5, and then divide by that same power, so divided by 9 over 5. When we divide by 9 over 5, it's the same thing as multiplying by 5 over 9. So what we have left is 5 over 9 times x to the 9/5. And then we're going to go ahead and evaluate from our bounds of 0 to 1. Now whenever you have a constant, you can take that outside when you evaluate. So we have 5 over 9 times, when I plug in 1 for x, we have x to the 9, or 1 to the 9/5, which is just 1. And then minus, when I plug in 0 into the function, 0 to the 9/5 is 0. 1 minus 0 is 1. 1 times 5 over 9 is going to give us the final answer of 5 over 9. Now for number 4, we have the integral from 1 to 2 of 3 over t to the 4th dt. Now in order to use the power rule, we have to move this exponent up top of the numerator and make it negative. So I'm going to rewrite it as the integral from 1 to 2 of 3t to the negative 4th dt. So now we can go ahead and use the power rule. Remember, 3 is just a constant, so I can take that outside of the integral as well. So I can rewrite it again as 3 times the integral from 1 to 2 of t to the negative 4th dt. Now the integral of t to the negative 4th, or the antiderivative, when we use the power rule, is going to be t to the negative 3rd over negative 3. Once again, we added 1 to the power and divided by that same power. We do have a 3 outside as a constant, so I'll go ahead and multiply by 3. So what we're left with, the 3's will cancel, and we'll have negative 1 over t cubed. Now I can go ahead and evaluate from the bounds of 1 to 2. So when I plug in 2 for t, we'll get negative 1 over 2 cubed, which is 8, minus, when I plug in 1 for t, we'll get negative 1 over 1 cubed, which is just going to be negative 1. The 2 negatives will cancel, and we'll get negative 1 over 8 plus 1, which is plus 8 over 8, and so that will give us 7 over 8. Now for number 5, we have the integral from 0 to 2 of x times 2 plus x to the 5th dx. Now before I evaluate, I'm actually going to go ahead and distribute the x into the parentheses. So then we'll get the integral from 0 to 2 of 2x, or 2 times x plus x to the 6th dx. So now I can go ahead and use the power rule. Now the integral, or the antiderivative of 2x, remember it's 2x to the 1st, so we add 1 to the power, divide by the same power, 2x squared over 2. The 2's will cancel, and so the antiderivative of 2x is going to be x squared. So we'll get x squared plus the antiderivative of x to the 6th. Once again, we add 1 to the power, divide by that same power, so x to the 7th over 7th. Let's go ahead and evaluate from the bounds of 0 to 2. So when I plug in 2 for x, we'll get 2 squared, which is 4, plus 2 to the 7th, which is going to be 128 over 7. And then minus, when I plug in 0 for x, we'll get 0 squared, which is 0, plus 0 to the 7th over 7th, which is also 0. Those will cancel, and I'm just going to go ahead and use a calculator to solve this. And you should get a final answer of 156 over 7. Now for number 6, we have the integral from 0 to pi over 4 of secant squared of t dt. Now in order to find the antiderivative, or the integral of secant squared, we need to think about what did we derive to get secant squared. Well, we derived tangent of x to get to secant squared of x, so we integrate secant squared to get to tangent. But instead of x, we have t, so the integral of secant squared is going to be tangent of t. Now we're going to evaluate from 0 to pi over 4. So when I plug in pi over 4 for t, we have tangent of pi over 4, minus, when I plug in 0 for t, we get tangent of 0. Now tangent of pi over 4 is 1, minus tangent of 0, which is 0. 1 minus 0 gives us 1. Now for number 7, we have the integral from 1 to 9 of 1 over 2x dx. Now before I evaluate, there is a 1/2 as a constant. I can take that outside of the integral. So we have 1/2 times the integral from 1 to 9 of 1 over x dx. Now remember, the integral, or the antiderivative of x to the negative 1st power, or 1 over x, is going to be the natural log of the absolute value of x. And then we do have the 1/2 out front, so I'll multiply by 1/2. Now we can go ahead and evaluate from the bounds of 1 to 9. Now 1/2 is just a constant, so I can leave that outside when I'm evaluating. So we get 1/2 times, when I plug in 9 for x, we get natural log absolute value of 9, which is just natural log of 9, minus, when I plug in 1 for x, we get natural log absolute value of 1, which is just natural log of 1. Now natural log of 1 is 0, that will cancel, and so we're left with 1/2 ln of 9. Now this most likely is an acceptable final answer, but if you want to simplify even further, you can, because using properties of logs, you can bring that 1/2 up top as an exponent. So we have ln of 9 to the 1/2. 9 to the 1/2, or the square root of 9, is 3. So that'll give us our answer of the natural log of 3. Now for number 8, we have the integral from 1/2 to the square root of 3 over 2 of 6 over the square root of 1 minus t squared dt. Now, first the thing I'm going to do, because 6 is a constant, I can take that outside of the integral. So I'll rewrite it as 6 times the integral from 1/2 to the square root of 3 over 2 of 1 over the square root of 1 minus t squared dt. Now this can be tricky, but remember that the derivative of inverse sine or arc sine of x is going to be equal to 1 over the square root of 1 minus x squared. This is in similar form, except that we have t instead of x. So the integral of 1 over the square root of 1 minus t squared is going to be equal to arc sine or inverse sine of t. So I'll write it as inverse sine of t. We do have 6 outside as a constant, so I'll multiply by 6. And then we can go ahead and evaluate from 1/2 to the square root of 3 over 2. 6 is just a constant, I can leave that outside when I evaluate. So when I plug in square root of 3 over 2 for t, we get inverse sine of square root of 3 over 2. And then minus inverse sine of 1/2. Now in order to evaluate inverse sine of square root of 3 over 2, we need to think about what do we take the sine of? Sine of what angle gives us square root of 3 over 2? Now remember that the range of inverse sine is from negative pi over 2 to pi over 2. So inverse sine of square root of 3 over 2 is going to be pi over 3. Now remember that sine of 2 pi over 3 also gives us square root of 3 over 2, but 2 pi over 3 is out of the range of inverse sine. And then we have minus inverse sine of 1/2, so what do we take the sine of, or sine of what angle gives us 1/2? And that's going to be pi over 6. So then we can go ahead and subtract those two fractions, so we get 6 times, I'll rewrite pi over 3 as 2 pi over 6 minus pi over 6. 2 pi minus pi is pi, so we get 6 times pi over 6, which is going to give us a final answer, the 6's will cancel, of pi. Now for number 9, we have the integral from negative 1 to 1 of e to the u plus 1 du. Now using properties of exponents, I can actually break this up. So we have the integral from negative 1 to 1. I'm going to rewrite it as e to the u times e to the first, or just e, times du. Now e is just a constant, so I can take that outside of the integral and write it as e to the first, or e times the integral from negative 1 to 1 of e to the u du. Now remember that the antiderivative of e to the x is e to the x, but instead we have u, so the antiderivative is just going to be e to the u. Don't forget we do have e outside the integral as a constant, so I'll multiply by that e, and then we can evaluate from negative 1 to 1. E is just a constant, I can take that outside when evaluating. So we have e times, when I plug in 1 for u, we get e to the first, which is just e, minus, when I plug in negative 1, we get e to the negative first, or 1 over e. Now I'm just going to go ahead and create one whole fraction inside the parentheses. So then we'll get e times, I'll rewrite e as e squared over e, so that we can have common denominators, minus 1 over e. E squared minus 1, we just get e squared minus 1 over e. Notice those two will cancel, and the only thing we're left with is e squared minus 1.